Imagine a 17.1 gigabyte model file on your laptop storage. That size makes local testing tangible, but doesn't prove speed. Now picture using it for private code or document work. That requires the file, working memory, and runtime to fit together. Qwen reports 61.7 on SWE-bench Pro, an agent coding test. That score makes real repository trials worth considering. A download can fit, yet answer slowly. Output speed is called throughput, and these sources provide no laptop throughput measurements. A model's learned numeric settings are called weights. Downloading them proves access, not whether your machine runs them well. So we'll label published facts, Qwen's own evaluations, and our practical analysis. That separation keeps your download decision evidence-based. Post-trained means refined after broad initial training for useful tasks. Qwen released this image and text model with Apache 2.0 weights. Imagine every prompt using one listed 64-layer stack. Qwen calls that a dense model because no expert routing structure is listed. A parameter is one learned numeric setting. Qwen lists 27 billion across 64 layers, explaining the model's 27B label. Suppose you ask about a diagram instead of pasting text. Accepting text, images, and video is called multimodal input. For example, Qwen sends an image and question through the same chat API. Your document tools can keep one interface. Some jobs need more internal reasoning than others. Reasoning effort is Qwen's high, medium, or low depth control, enabled by default. Generated text is counted in small pieces called tokens. Qwen warns lower reasoning effort can cause retries, increasing time and token use. A runtime is the software that loads and serves a model. Qwen supports transformers, vLLM, SGLang, and TokenSpeed using current versions. The license, learned weights, examples, and smaller files are available. The remaining question is how the 27B design spends computation. Picture information crossing 64 processing steps. Each step is a layer, and every input token passes through all 64. Attention means a layer carries information across a sequence. Qwen labels 3 repeating layers per block as linear attention. Qwen calls those linear attention layers Gated DeltaNet. Each then uses a feed-forward network, an added processing step before continuing. Every 4th layer uses full attention. Its heads are parallel attention channels, 24 attention heads, and 4 key value heads. Picture a 4-step loop. 3 gated DeltaNet layers, then 1 full attention layer. 16 loops produce all 64 layers. That count gives 48 linear attention layers and 16 full attention layers. It explains the architecture, not laptop speed. Imagine training the model to forecast several upcoming tokens, not only one. Qwen calls this multi-token prediction and reports no isolated gain. A context window means everything the model can read and produce at once. The native limit is exactly 262,144 tokens. For an unusually huge project, Qwen documents extension to 1 million tokens. YARN is the position scaling method used beyond the native window. Leaving that scaling on for short prompts can backfire. Qwen warns static YARN may reduce shorter text performance, so enable it only when needed. Suppose you need a smaller download. Quantization stores model values with fewer bits. Here, that means choosing a lower bit GGUF file. BF16 is the published 16-bit package, sized at 54.7 gigabytes. Your runtime still needs space for prompts and working state. The 4-bit Q4KGEM file is 17.1 gigabytes, roughly 1/3 of BF16. That sharply lowers the storage hurdle. The 5-bit Q5KK file is 19.8 gigabytes. It uses 2.7 more gigabytes than Q4KK/PONAM for higher bit storage. The 8-bit Q80 file reaches 29 gigabytes. More precision therefore gives back much of the storage saved by 4-bit packaging. The published 2-bit files range from 9.01 to 10.7 gigabytes. They minimize storage most aggressively. Downloading is only step 1. Runtime memory means the total space used while running, which these file sizes don't report. Suppose a later reply needs earlier reasoning. Preserved thinking keeps those reasoning blocks and helps reuse the KV cache, or saved context state. The 262,144 token limit describes supported sequence length. It doesn't promise that maximum context fits comfortably beside the model file. So test the real combination: chosen file, runtime state, and intended context. Free storage alone cannot answer that fit question. Inference means running the model to generate answers. Smaller files make laptop inference plausible, but these sources prove neither speed nor maximum context operation. A benchmark is a standardized capability test. Qwen's reported benchmarks are this packet's strongest evidence, so the source attribution matters. Imagine the same model with different tools and limits. That surrounding evaluation setup is the harness, and it can change results. Qwen reports SWE-bench Pro rising from 53.5 to 61.7. That is an 8.2-point gain under its refined setup. In that setup, the higher score means more software tasks completed. It is not a universal success rate for your repository. On Terminal Bench 2.1, Qwen reports 73.0 versus 63.4. The 9.6 gain supports testing terminal work. On NL2 repo-bench, Qwen reports 42.3. That tops 36.2 and 41.1, supporting repository generation trials. On CoWorkbench, Qwen reports 70.7. That exceeds 61.0 and 65.1, supporting long task trials. On IFBench, Qwen reports 79.5. That is barely above 79.1, but well above 69.1. For OS World verified computer use, Qwen reports 84.3 versus 63.9. That 20.4 gain supports testing visual computer tasks. For WebArena verified browser use, Qwen reports 64.8 versus 48.8. That 16-point gain supports browser agent trials. Across Qwen's table, every listed comparison beats its 27B predecessor. The practical signal spans coding, computer use, and long tasks. Change prompts, tools, context, retries, timeouts, or graders, and scores may change. Compare models only under matching evaluation conditions. Temperature and top P control how next words are sampled. Qwen used 1.0, 0.95, and a 256,000 window. Qwen says it corrected problematic SWE-bench Pro tasks and reran baseline models. So compare numbers within this refined table. An in-house evaluation is created by the model maker. Qwen labels 3 benchmarks in-house, making independent replication especially useful. A model grader uses another AI model to judge answers. Qwen names GPT-4o and GPT-5.4 in 2 evaluation setups. Laptop performance needs generation rate, power, heat, and first response delay. The packet reports none, so benchmark your exact machine. Smaller files may behave differently, but the packet gives no Q4, Q5, and Q8 quality comparison. Test outputs before choosing. A vision encoder turns images or video into model input. This one has 27 layers, adding processing beyond text generation. Pre-processing decides which video frames reach the model. For hour-scale video, Qwen recommends raising limits for higher frame rate sampling. Open weight means builders can access the learned weights. The sources support a capable compact release, not independently proven frontier laptop performance. Try it if you can compare file formats, limit context, and measure your own coding tasks. One headline score isn't enough. Start with Q4 cache M at 17.1 gigabytes or Q5 cache at 19.8. Both are concrete storage checks, not memory guarantees. Use a current supported runtime, transformers, vLLM, SGLang, or TokenSpeed. Qwen says versions affect compatibility and performance. Begin with ordinary prompts inside the native window. Enable 1 million token YAO-RN only when needed, because shorter text performance may fall. Run your real workload and record completion quality, retries, delay, and memory. Published benchmarks cannot answer those machine-specific questions. The model makes advanced local coding and vision experiments tangible, but frontier on a laptop remains a hypothesis your measurements must test. Watch for independent quality comparisons and laptop speed tests across context lengths. Those results will decide whether the promise is practical. If you test it, publish the quantization, context, runtime, and machine. Those details let other builders reproduce your result.